So in this video, I would like to introduce two important sets that are associated with any given matrix. The set which is called the matrix's null space, and the set which is called the matrix's column space. And today we're going to focus on determining if a single given vector is inside the null space of a matrix or if it's inside the column space of a matrix. And then we will study null space and column space in a slightly more thorough way in a couple of lessons from now. So what do we mean when we talk about the null space of a matrix? The null space of a matrix is the set of all the vectors which become zero after they are multiplied by the matrix A. So the null space is the set of all vectors X that satisfy that when you multiply them by the matrix A, the result of that is the zero vector. All vectors that become zero after A is applied. Or put another way, all of the vectors that are destroyed by the matrix A. So if someone gives you a matrix A and they give you a vector X and they ask you, is this vector X in the null space of this matrix? Answering that question is really quite straightforward because all you have to do to answer that question is check see, is this vector X destroyed by the matrix A? If I take this vector X and multiply it by the matrix A, do I get the zero vector as the result? So for this particular matrix, where A is equal to -2, 1 for -2, and the vector X is equal to 3, 6, let's go ahead and multiply this X by this matrix to see what happens as a result of that action. So using the standard dot product process, if I multiply the first row by this column vector, I get -6 plus 6, which is indeed equal to 0. Similarly, if I do the second part, where I dot the second row times this vector, then I get from that action 12 minus 12, result again 0. So I have applied the matrix A to this vector, and I have gotten 0, 0 as the result. And my conclusion would be that, yes, this particular vector is in the null space of A. This particular vector is destroyed by the matrix A and is turned into 0. Now, something that will be important for us to remember going forward is that the null space of a matrix is never empty. The null space of a matrix always has at least one vector inside of it, and that is the zero vector itself. So in other words, what we're saying is that if you apply the matrix A to the zero vector, the result of that is also going to be the zero vector. A applied to 0 is also still going to be 0. Therefore, 0 is in the null space. And this completely makes sense as a result. Like if your matrix has whatever entries, 4, 3, 5, 2, 0, 1, if you multiply that by the zero vector, the zeros in the zero vector will just completely cancel everything out. So you will automatically, no matter what, end up with 0 as the result. So the null space of a matrix A always contains the zero vector. Sometimes you will hear some language associated with this fact. If you are thinking about an equation of the form A times some vector resulting in 0, then if you put the 0 vector in X's position, this equation will always be satisfied. So when you're in this particular context of thinking about your matrix turning stuff into 0, sometimes the 0 vector will be referred to as the trivial solution to this equation because 0 satisfies this equation. 0 is a solution to this equation, but it's because it's always the solution no matter what, it's not really giving you a lot of data about your matrix A or any of its properties. So the 0 vector, sometimes you'll hear it called the trivial solution. Now, as we have been developing this definition of null space, some of you may have noticed that this definition of null space is quite similar to the definition of kernel that we introduced several videos ago. This lesson, domain, codomain, kernel, and range of a linear transformation. We talked in this section about the kernel of a transformation, and the kernel of a transformation was, again, everything that becomes 0 after t is applied. Or in other words, everything that is destroyed by the transformation, all the data that is lost, all the data that is compressed when the transformation is applied. That concept of kernel for a linear transformation truly is identical to this concept of null space for a matrix. Particularly if you have a linear transformation and you find the matrix A that represents that transformation, the same way we did back in this lesson, representing linear transformations as matrices. If your linear transformation has been represented as this matrix A, then the kernel of the transformation is exactly the same as the null space of that matrix. So you should understand these two concepts as being, again, interchangeable. The null space of the matrix A is the same thing as the kernel of the transformation T, assuming that A is the matrix that represents T. So to take a step back, remember this theme that has been present in the whole class. The theme that, from a computing point of view, representing everything in terms of matrices is the wisest possible move, because matrices are very efficient data structures, both in terms of memory and storage, and in terms of speed of computation. So if we can take any concept, every concept, and rewrite it and express it in matrix form, then that allows us to deal with those concepts most efficiently. So we can represent transformations as matrices, and we can also represent kernels of transformations as null spaces of matrices. And so dealing with this is going to be easier and faster from a computing point of view. Another piece of terminology associated with matrices is this idea of column space. For a matrix A, the column space of a matrix are all of the vectors B such that the equation AX equals B has at least one solution. So, put another way, the column space consists of all the vectors that can actually be produced by the matrix. All the vectors that can be achieved or produced by applying the matrix A to whatever vector in the domain. So once again, you may already be noticing a connection between this definition and one of the definitions that we arrived upon earlier in this class, the definition of range. The range of a function, the range of a transformation, is everything that can be produced by this transformation. And similarly here, when we talk about the column space of a matrix, we are talking about all the vectors that can be produced by that matrix. So let's get some practice checking to see if a single given vector is in the column space of a given matrix A. So for example, someone says, here's the matrix A. It has 3 rows and 2 columns, and the entries are 2, 4, 3, 0, -1, +1. I have the vector B here, and it's a two-dimensional vector containing the entries 3 and 0. Is this vector B in the column space of this matrix A? And without doing any calculations, without doing any real work at all, just looking at this problem, I can answer this question immediately, and I can immediately conclude that no, this B is not in the column space of this A. The reason that I can immediately detect an issue with this vector B is that the vector B is not the right length to be in the column space of the matrix A. If I think about the equation A times X equals B, and I remember that this matrix A has 3 rows and 2 columns. In order for this product to be defined, the inputs, the vectors X, have to be 2 entries long. And then when this product is calculated, the result has to be
3 entries long.
So the column space of this matrix contains vectors that are 3-dimensional. The column space here is a subset of R3. In other words, all vectors in the column space of this matrix have 3 entries. So the vector B given here, only 2 entries, is automatically disqualified from being in the column space just because it is the wrong length. Now, let's go ahead and fix that issue, and let's suppose that I have the same matrix A as before, but this time my vector B is the 3-dimensional vector 0, -6, 3. Let's now ask ourselves the question if this B is in the column space of the matrix A. So I'm going to answer the question whether the equation AX equals B has a solution. Is it inconsistent, having no solutions, or is it consistent, having at least one solution? To answer this question, I could take the same approach that we've been using in the past several lessons of converting this equation into an augmented matrix, row reduce that matrix, and then inspect the result to see if the result would correspond to having a solution or not having a solution. So let's go ahead and convert this to an augmented matrix. A augmented with B. And A augmented with B in this case would be the matrix 2, 4, bar 0, 3, 0, -6, -1, 1, 3. Setting up the augmented matrix that represents this matrix equations being the same things as systems of equations, just expressed in a slightly different format. Now, if you have a graphing calculator on hand, you are more than welcome to do the row reduction via calculator. Just for the folks who don't have the graphing calculator, as usual, I'm going to go ahead and do this process manually. So I'm going to go ahead and swap row 1 and row 3 just to pop this -1 into the top row because that'll make it easy for me to cancel out the rows underneath. Then I'm going to go ahead and eliminate these pivots underneath -1 in the first column. So I will add 3 copies of row number 1 into row number 2, and I will also add 2 copies of row number 1 into row number 3, because this action will allow me to eliminate the 3 right here and this 2 right here. That's going to turn row 2 into 0 in this position in the first column, then 3 in the second column, and then 9 plus -6, 3 here in the back. And then if I do the same thing here with the third row, I get 0 here. I get 2 plus 4, which is 6. And then I get 6 plus 0, which is also 6. The last thing that I would do to process this augmented matrix is I would deal with this entry in the third row, second column, this 6 underneath the pivot 3 in this matrix. So let's go ahead and add -2 copies of the second row into the third row to eliminate that 6 under the pivot. And so that cancels out all of the entries in the third row, giving us an answer of 0, 0. So if I think about this in terms of a system of equations, or if I think about this in terms of this matrix equation, I'm asking the question, does this equation have a solution or not? So if I just for a moment say that these first entries are the variables, I'll call them x1 and x2. I do have 3 equations and 2 variables here, but because the last row has completely vanished, I'm only getting 2 meaningful equations from the augmented matrix I'm looking at. -x1 plus x2 equals 3, and I'm getting 3x2 equals 3. And I don't have to solve this. I only have to recognize that this system has a solution. I'm not getting any impossible requirements here like 0 equals 5 or 0 equals 6. I'm getting 2 equations that both can be solved for x1 and x2 perfectly well. So this matrix equation, ax equals b, would have a solution. So I could conclude that this b is in the column space of this matrix. Now, by contrast, suppose that for that same matrix A, I change the vector B, and now the vector B is 6, 3, 4. Let's go through that same process and check see if this vector B is in the column space of the matrix A. So once again, I'm going to acknowledge the fact that what I'm trying to figure out is whether the equation AX equals B has a solution. So I can use the augmented matrix and I can use row reduction to answer that question. Performing the same kind of actions that we did last time, the same kind of operations of swapping rows, do this same operation of scaling and adding rows together. So now look what happens when I move to eliminate this pivot underneath 3 in the third row. In the outputs column, I get -30. -30 plus 14, I get -16. So if we think about what this augmented matrix would be telling us in terms of the solution, if I translated this augmented matrix back into a system of equations, the first equation is fine, -x1 plus x2 equals 4. The second row corresponding to the second equation is also fine, but there's a big issue with the third row, right? The third row is demanding that 0 is equal to -16, which is impossible. We've ended up with a pivot in the outputs column of the augmented matrix. This AX equals B equation has no solution. This is an inconsistent system of equations. So as a result, we must conclude that this B is not in the column space of this matrix A. This B is not in the set of vectors that this matrix A is capable of producing. So to reiterate what I mentioned earlier, this definition of column space of a matrix is virtually identical to our definition of range of a linear transformation that was given earlier in the class. Range being all the possible outputs for your linear transformation. And in particular, if your matrix A is a representation of your transformation T, then the column space of A is identical to the range of T. Those should be considered exactly the same, identical, interchangeable ideas, column space of a matrix and range of a transformation. So just to summarize that, and to summarize some of the other results that we have achieved through this video, we have this idea of a linear transformation, which can be represented as a matrix. And a matrix can also be understood as a linear transformation of vectors. So these two concepts are interchangeable. The domain of a linear transformation, the kinds of vectors that can go into a linear transformation, corresponds to the number of columns of your matrix. Because the number of columns of your matrix completely determines what type of vectors can be multiplied by the matrix A. So for example, if your matrix A has 2 columns, then it is able to multiply vectors that have 2 entries. So the number of columns of your matrix corresponds to the domain of that transformation. Now similarly, the codomain of the transformation is determined by the number of rows of your matrix. The codomain of a transformation is the type of the outputs that are produced by that transformation. And when you're thinking about transforming vectors by multiplying by a matrix A, the type of vectors that are produced is determined by the number of rows of the matrix. If your matrix A has 3 rows, then it is producing vectors that have 3 entries. So the number of rows of your matrix determines the codomain of the associated transformation. Similarly, when we talk about the range of the linear transformation, the vectors within the codomain that can actually be produced by the transformation, that corresponds to what we call the column space of the matrix, the vectors that can be produced by multiplication by this matrix. And similarly, this idea of kernel of a linear transformation corresponds to this idea of null space for a matrix. All the vectors that are destroyed when the matrix A is applied. All the vectors that are turned into 0 when the matrix is applied. Now, just to emphasize again, when we're talking about matrix multiplication, the domain is determined by the number of columns, and the null space is a subset of that domain. The null space is a subset of the domain because the null space are vectors that are going into the transformation. The null space are vectors that are being affected by the matrix A. Whereas here in the codomain, which is determined by the number of rows, the column space is a subset of that codomain. The column space is everything that the matrix is actually capable of producing. So the column space is about outputs, whereas the null space is about inputs. So that concludes today's lesson. Today we defined null space for a matrix A, and the null space for a matrix A is just all the vectors that are in the domain of A, which happen to become 0 after the matrix A is applied. And if you need to check if a certain vector is in the null space of a matrix, all you have to do is multiply that vector by that matrix and check see if the result is equal to 0 or not. The idea of null space of a matrix is equivalent and interchangeable with the idea of kernel of a linear transformation. So you might hear me using those terms interchangeably as we progress into the next several lessons. Now, the column space were the set of all the vectors in the codomain that the matrix A could actually produce. All of the vectors in the codomain such that AX equals B has at least one solution. It can be produced by this matrix somehow. The easiest way to check if that B is in the column space is to set up the augmented matrix corresponding to the equation AX equals B. Then row reduce that matrix, and by examining that row reduced augmented matrix, check see if that system is consistent, if there is at least one solution to the system, or check see if the system is inconsistent, if somewhere the system of equations is demanding something impossible, like 0 equals some non-zero value. If you get an impossible condition like this one, then AX equals B has no solution, so B is not in the column space of the matrix. And column space of a matrix is equivalent to this concept of range that we talked about earlier for linear transformations. Column space is the same thing as range.